So, in the previous video we had seen how we can use an implicit function to plot a streamline. Now, plotting a path line is relatively hassle free because we do not need to do an explicit plot, but we do not need to do an implicit plot, but we can also represent that through an implicit plot. Let us see how. So, for the given question, we have been given, so we recall that the velocity was x and minus y t. So, to obtain the path line, we have dx dt is equal to x, implying log x equal to t plus c. Using the boundary condition, at t equal to t 0, x equal to x 0, we have ln x by x 0 is equal to t minus t 0. Similarly, we have dy dt is equal to minus y t. This implies dy by y is equal to minus t dt, essentially saying log y is equal to minus t square by 2 plus c. Using the condition at y at t equal to t 0 is equal to y 0, we obtain ln y by y 0 is equal to minus of t square by 2 minus t 0 square by 2. So, essentially as time evolves, we can simply note from these two equations that x is equal to x naught exponential of t minus t naught and y is equal to y naught exponential of minus 1 by 2 t square minus t 0 square. So, these are the two expressions. So, these are the explicit expressions. This is how the equations are parameterized as per time. We can easily set the initial time to be whatever we like and the initial location to be whatever we like. So, let us open a new file. We copy this bit because we will require to plot the quiver. We call this as the path line. So, let us see if it works. Perfect. So, we have to do a draw now because otherwise the computer is waiting. If we do not do a draw now, the computer does not reveal the plot until the loop is finished, and hence we could see directly the final answer. So, the draw now causes the computer to draw the plot right when it receives the data. Okay, this is how it looks. So, then on top of this, we can write down now the equation of the path line. So, we have the following. Let us define x 0 and y 0 outside the loop, and y 0 equal to 1, and t starts from 0. And so, we do hold on top of this figure, we have to now plot the particle. So, plot the x and y coordinates. So, it is x 0 times exponential of t minus t 0, okay, comma y 0 times exponential of minus 1 by 2 times t square minus t 0 square. And then we also need to define what t 0 is. Okay, with this plot, we will use this explicit representation for the velocity for the particle location and plot it on top of the quiver plot. So, we have to represent the point as a in terms of a marker, because we cannot see a single point in the figure. So, we will declare whatever the points are as the following. So, what we are observing here is that the particle is exponentially going towards the x, and hence the limits are increasing, but we need to keep this bounded. So, how can we do that? We will show you. So, here we need to first define how the particle will look like. It will look like some kind of a marker. So, we say it is OK. OK implies the marker will be circular, having a black color, and the marker face color will be black. Okay. So, this is how we define this, and then we must set that the x limit and the y limit while plotting should not exceed, should range from 0 to 5. Similarly, the y axis should also range from 0 to 5. Now, once we do this, we can run the program to plot the quiver plot and the path lines simultaneously and the particle trajectory simultaneously. This is not the path line, the path line is a locus, but first we will plot the particle paths and then we will go to the path line. So, let us see how it looks. This is how the particle is going. Okay. So, maybe to make it look smoother, we can increase the number of time intervals and we can decrease the pause. Now, the plot should look much smoother. There you go. So, the particle is following the quiver plot, and at each point of time the particle is moving tangentially to the local velocity. Alternately, we can change the initial condition. Let us say we have a particle originating at 2, 3 at t equal to 0, then we have this. Okay. Clearly, the particle moves in the direction of the quiver. Alternately, we can increase the bounds and correspondingly increase the limits of plotting if we are interested to have a look at how the particle this is how it looks like. So, this is the trajectory of a single particle moving through the velocity field as shown. So, now how do we obtain the path line? So, we have to eliminate the final time. So, log of x by x naught is equal to t minus t naught, and similarly log of y by y naught is equal to minus half t square minus t 0 square. We set t 0 equal to 0 because all the path lines will be such that it travels at x naught and y naught at t equal to 0. Therefore, we have log x by x naught is equal to t and log of y by y naught is equal to minus half t square, but t is equal to this. So, this becomes minus half log of x by x naught whole square. So, the function that we have becomes log of y by y naught plus half log of x by x naught whole square equal to 0. So, then we can use that idea once again, that if we have any function f, an implicit function f defined as this, then setting the level of f to 0 will give us the path line. So, let us set x naught equal to 1 and y naught equal to 1 again, and after plotting the trajectory we also want to plot what the actual path line also looks like. So, let us do this. So, we have contour x comma y comma log of y by y naught plus half times log of x by x naught whole square, and we have to plot the 0 level of the function as defined. So, there you go. The green line represents the path line obtained from this equation, and we can clearly see that the particle is following that given trajectory. So, in this way we can define the path line and plot the path line, and we will see how different initial conditions give us different different path lines. The errors are because we have not resolved the domain appropriately, which we can do very easily. So, let us define the domain from 0 to x goes from 0 to this and y goes from this. If we take a bunch of points, then we do not need to pause anymore. There you go. So, the black point initiated at x equal to 1 and y equal to 1, and it is moving along the path line as the velocity is continuously changing in time. The velocity is not fixed in time, the velocity is changing. This is how it looks. So, this example showed us that we cannot simply plot using less points. Sometimes we need to increase the number of points, but anyway, the point is we can define the mesh, we can define the vector plot, then based on the ideas of the implicit function f, we can find the contour of f equal to 0 to yield the path line, and the trajectory found out using the parameterization of time lies exactly on the path line as expected. There is nothing fancy about this, there is nothing sacrosanct about this, but one should be able to visualize how the trajectory and the path line are related by actually plotting various problems that you will do in parts of your assignments or as a part of coursework during the lectures. One should go home and do this on open source softwares like Octave and then see how it looks like. This gives you a much better feel of what is really going on. Then finally, we move on to Streakline. So, if you recall, Streakline is defined as the locus of particles at a given time which were injected at some fixed point at all times less than t. So, if we have a nozzle here, this is the flow, then this particle was injected say at t equal to 5, and because of this, this is the path line of this particle. Then some other particle was injected at t equal to 4, it comes over here. Some particle at t equal to 3 comes over here, t equal to 2, t equal to 1, and at t equal to 0 it is just escaping the nozzle. So, the streak line would look something like this, all the lines connected. This is how the streak line would look like. So, essentially we have to plot all the path lines one after the other, and then all the path lines, the endpoints of those path lines injected one after the other will give us the streak line. So, how does the streak line look analytically? Let us do that first. So, the solution for this, let us write it again. Okay. In this particular solution, we now have to eliminate the injection time. So, we have to eliminate T naught. In order to find the path line, we had to eliminate T, but here we have to eliminate T naught. So, what do we have? We have x by x naught is equal to exponential of T minus T naught. So, essentially we can do a log and write it as following. And then we have log y by y naught is equal to minus half t square minus t 0 square. So, then t 0 is equal to t minus log of x by x 0, and thus using this expression in this, we obtain log of y by y 0 times minus 2 is equal to t square minus t 0 square. So, minus t minus log of x by x naught whole square. So, this is equal to t square minus t square plus 2 t log of x by x naught minus log of x by x naught whole square. So, this is equal to 2 t log of x by x naught minus log of x by x naught whole square. So, essentially we can modify this as follows: log of y by y naught square. So, we have taken this 2 up and multiplied by minus 1 is equal to minus 2 t log x by x naught plus log of x by x naught whole square. So, this the equation is log of y by y 0 whole square minus log of x by x naught whole square plus 2 t log of x by x naught. So, if we define this as the level function now and set the contour of f equal to 0, then we should be able to obtain the path line, we should be able to obtain the streak line. So, let us copy this code, let us save this as streak line, but now we do not want just one particle, we need to have many particles. So, let us change this. Okay. So, for each of the particle, as time progresses, there will be a new particle injected into the domain. So, let us write here particle index equal to 1, and then we will increment particle index as time goes on. So, at t equal to 0, there is only one particle. As t increases, we inject more and more particles. So, for I equal to 1 to particle index, we will do the path line, we will do the particle trajectory. We do not need this. So, for each particle index, we will plot the particle, where now t 0 has to be appropriately chosen. Now, so what is t 0? As t increases, for each successive particle, the t 0 will be different. For example, here the t 0 for this particle was 5, the t 0 here was 4, and so on. So, as the time progresses, we inject a particle. So, this t 0 for each particle should be changing. Okay. So, here we should create an array of t 0, which will look like exactly this array, and here instead of t 0, we should have t 0 of I, because for the first particle the injection time will be t equal to 0, for the second particle the injection time will be t equal to 0.1, for the third particle it will be 0.2, and so on. So, as time progresses, we have to do this, and then at the end of this, because the time loop will progress, for the next time we need to have a loop which goes over 2 particles instead of just 1 particle, and hence particle index should be equal to particle index plus 1. Okay. And this can come outside this hold off block. Okay. So, let us see how this looks. My bad. So, t 0 is, there is an error here. Okay. So, it is undefined near line 22. So, t 0 a was the array, we have only defined it as t 0. Let us decrease the number of points, too many points. Okay, this is how multiple injections look like. But now we want to make the points have different colors, because we want to identify how the particles look like. So, we can do that very easily. So, we can define the color array as following. So, green, so the blue, black, green, magenta, these are the various colors that we want to use. Appropriately, we also want to color them. We have repeated this twice. So, with this we can then set the various colors for the particles by writing here simply. So, but I cannot loop on continuously. So, we have to do a modulo function. We have 5 entities here. So, you have to cyclically assign all the colors. For doing a cyclic assignment, we have to do this kind of mode. Similarly, for filling the marker, we will do this. So, now we see that as time progresses, particles of various colors are being injected into the domain. So, this helps in visualizing how the whole thing looks like. We can take the injections at finer times. This is how a continuous injection of dye would look like in the domain. So, now we would want to verify whether the equation of the streak line at t equal to 5 is correct or not. Okay. So, this is the equation of streak line at t equal to 5. This is the final time. So, let us see how to do that. We will stop the program. The program can be stopped at any time by pressing Ctrl C in the command window. That is a universal indication of stopping the program. So, at the end of this loop, we will be at t equal to 5. So, on top of whatever plot we have, we should simply plot the implicit plot of the function f and draw the 0 contour of the level set function f. So, let us do hold on and then contour x comma y comma log y by y 0. So, this is simply 2 times this minus of log x by x 0. The log is squared, this is not the same as 2 log, plus 2 into t times log x by x 0. So, we will reduce the time because we have seen how it looks like. So, there is no point looking over and over again at the same animation. So, the program will do all the particle injections and then in the end it will show us the streak line. The streak line will be the joining of all the points and the line that we have plotted as a contour, as a 0 level contour. So, I forgot to set the 0 level here. So, if we do not set any level or any number, it will show us all the values of it will show us all the values. So, we need to specify that we do not want all the values of the function f, we just want the 0 level contour. Let us increase the resolution in the x and y direction. I have to also change the y limit. Okay. So, there we are. By increasing the resolution further, we will be able to plot the actual trajectory. And this clearly shows that by making use of implicit functions, one can plot these kind of locus. So, the implicit function is very important to plot these locuses and so on. And by making extensive use of this kind of functions, we can plot the streak line by. So, the streak line was essentially the joining of all the trajectories, but the streak line essentially is also the implicit function after eliminating the initial time, because we want to find the trajectory with respect to the initial point. So, once the initial point has been parameterized, here we have eliminated the initial times, and then at the final time we have then sort of obtained the xy locus. Okay. So, with this we conclude this small session on making such kind of plots, and hopefully you will go back and teach the students how such kind of plots can be made, because in pedagogy it is very important to make the students appreciate that they don't have to blindly take our word for it. They can make the trajectories, they can make the plots, they can visualize the flow fields, they can find the iso lines, and through this the learning is enhanced in the sense they can really then apply whatever they have learned to more real life situations, because in real life situations, suppose one has velocity data through PIV, then they can be in a much better position to analyze the data, to understand what is going on, to understand whether the line that they see in some data or some experiment is a streak line or a path line. So, these are the kind of numerical experiments which will expose them to such kinds of mathematical entities and thus enrich their learning. With this, we conclude this session, and I will see you next time. Thank you.